Welcome to the next lecture on heat transfer. Till now, we saw zeroth law, first law, second law. We saw the application of this PV diagram, TS diagram. Then we moved into cycles, different types of cycles. We saw Otto cycle, Diesel cycle, then Rankine cycle, Brayton cycle. We saw all these cycles. We also found out in all these cycles how do we find the efficiency, thermal efficiency of the process. And friends, in this entire course, there are only two things. One is how do we apply heat or how do we extract heat, or how do we apply work or how do we extract work. These are the two things. If we wanted to understand that, we have to go through step by step and understand the fundamentals. Then we move to the technology which is associated with that. From that understanding, we will now move towards a new topic, heat transfer. In this topic, we will try to cover what is heat transfer, what are the different modes of heat transfer, conduction, Fourier law, thermal conductivity. Then we will try to see plain wall conduction, composite wall conduction, cylinder conduction. So, by giving the shape, how does the conduction happen? Then comes convection, free convection and forced convection. Finally, we will try to see radiations. Many a times, if you see, when the heat has to be removed faster, we try to put a fan very close to it and we try to extract heat, isn't it? So, that is in the forced convection. Free convection is you leave it in the free atmosphere. Yesterday, when we were trying to feed our pet, so we cooked food and then it was very hot. He was very hungry. So, we had to find out ways and means how we can cool such that our pet can have the food. So, there comes the concept of free convection and forced convection. Heat transfer refers to a phenomena in which heat or thermal energy is transformed from one region to another. It can be higher to lower or lower to higher, whatever it is. So, it is only a heat transfer or a thermal energy transfer happening between two regions. Deals with the study of rate. So, moment there is, I gave you an example of cooling food for my pet. So, I wanted to do faster. So, I have to now work with time. So, the transfer of heat is 1, the rate of transfer of heat is 2. So, deals with the study of rates at which the exchange of heat takes place between a hotter surface and a cold receiver. See, if you can take an example, you take a box which is at 60 degrees Celsius and you have an atmosphere which is around about 30 degrees Celsius. You see the heat transfer, what happens? 1, you see the rate at which the heat transfer happens. That means to say, when does 60 degrees become 30 degrees? Then you try to have 60 degrees a vessel and also have outside temperature 60 degrees. Now, you see the rate. So, you see there will be a different phenomena. The object whatever you kept here, maybe a cooked food in a steel vessel in a room where the atmosphere temperature is 30 degrees, where the atmosphere temperature is 60 degrees. The food is the same, the steel vessel is the same, the surrounding is the same, the air is constant, it is not moving. You see there will be a difference in the exchange of heat. So, the rate is very important. If two bodies at different temperatures are brought in thermal contact, the heat flows from a hot body to a cold body or relatively cold. So, it can be 60 degrees, it can be 50 degrees. So, there will be a heat transfer from 60 to 50. The net flow of heat is always in the direction of decrease in temperature. Thus, heat is defined as a form of energy which is in transit between hot source and a cold receiver. Can we do it ulta from a cold to hot? Yes, you can do, but hot to cold happens naturally. If you want to do inverse of it, you have to apply energy. Right? The transfer of heat depends upon the temperature of the body. So, you can see here there is a log which is set in fire. So, just outside the fire there is, you can see the waves, electromagnetic waves. So, these waves there is radiation, the energy transferred by electromagnetic waves. So, here it is convection, energy transferred by molecular motion. So, from here it can radiate, and then what you do is you operate a fan on top of it. So, here what happens, the energy transfer is done by molecules, and then the third one is you keep a red hot rod which is attached to your hand. You see conduction, the energy transfers by direct contact. So, this is the difference between convection, conduction and radiation. So, thermal imaging cameras work on IR, which is electromagnetic waves they try to capture. That is what is used in your airports. When the passenger keeps moving, there will be IR camera which tries to check what is the body temperature from a very far off distance. So, that is done by radiation. The next thing is convection, is the molecular transfer, the energy transfer by molecular motion. The conduction is this. Modes of transfer. Heat transfer is a vital area of study in thermodynamics, concerned with the movement of thermal energy due to a temperature difference. Delta T difference plays an important role in the rate. If the delta T is high, the rates also majority of the time can be high, the rate of heat transfer can be high. It plays an essential role in numerous natural phenomena and engineering systems such as warming of the earth by sun, operation of engine and refrigerator, designing of a thermal insulation in a building, cooling of electronic devices. So, all these things are examples where heat transfer are very important. Friends, the IC chip today which is used in the processor always puts a restriction. It is not because the feature size cannot go small, it is for that feature size what will be the heat rejection and what will be the cooling, that puts a challenge. So, people are looking forward for making cooling which is very efficient in small scales. So, micro scale heat transfer is a big research topic in the area of heat transfer. Heat always flows spontaneously from a higher region to a lower region until the equilibrium is reached. We have seen the three modes of heat transfer, and each mode operates through physical mechanism and dominated under specific circumstances. So, conduction is the transfer of heat from one part of your body to another part of the same body, or from one body to another body which is in physical contact with. So, that is conduction. Convection is a transfer of heat from one point to another within a fluid. It can be a gas or it can be a liquid by mixing a hot and a cold proportion of the fluid. The convection is restricted to flow of heat in fluid. Radiation refers to the transfer of heat energy from one body to another through space by electromagnetic waves. So, this is important. Conduction. Conduction refers to the mode of heat transfer in which heat flow through a material medium occurs without actual migration of particles of the medium from a region higher to a region lower. Conduction occurs by the migration of molecules and more effectively by the collision of the molecules vibrating around relatively fixed position. So, we are talking about dipole-dipole movement which happens. So, when there is a migration of molecule and more effective by the collision. So, assuming that there are two molecules, so they try to collide with each other and try to bring in heat. by the collision of molecule vibrating around its relatively fixed position. So, that is how heat transfer happens. There is a steady state unidirectional heat conduction in solid. Steady state heat flow means the temperature at any location along the heat flow path does not vary with time. Rate of heat transfer does not vary with time. The temperature varies with location, but not with respect to time. So, that is one of the most important thing. Steady state unidirectional heat conduction in solids. Temperature varies with location, but not with time. So, Fourier's law is an important law when we talk about heat transfer. Fourier's law states that the rate of heat flow by conduction mode is very important. The rate of heat flow by conduction through a uniform material is directly proportion to the area normal to the direction of heat flow and the temperature gradient in the direction of the heat flow. Two important points: the rate of heat flow by conduction directly proportion to the area normal. Suppose it flows like this, area normal, this is an area, is directly proportion to the area normal to the direction of the heat flow and the temperature gradient in the direction of the heat flow. So, proportion to the area normal to the direction of heat flow, right, and the temperature gradient in the direction of heat flow. Fourier law states that the time rate of heat transfer through a material is proportional to the negative gradient in temperature and to the area. So, this is another way of putting forth the same law. The temperature gradient is what you have of this thing. You try to measure temperature here along the length. The rate of change of temperature with displacement in a given direction. Here the temperature gradient is negative, since with an increase in N there is a decrease in T. The temperature decreases in the direction of heat flow. So, this is what is the pictorial representation of the Fourier's law of conduction, heat conduction. So, conduction area equation can be represented as Qx is equal to minus negative flow K times, K is a thermal conductivity, or you can take it as a constant for a given material, K, and then A is what we have been time and again saying. Qx, the heat, the rate at which the heat flow is equal to minus negative flow, K is a constant, A is normal to the area, dt by dx. So, the Q is the rate of heat flow slash transfer by conduction. Q is the rate of heat flow transfer by conduction. K is the thermal conductivity of the body material. So, it is represented as watts per meter Kelvin. A is the cross section area normal to the direction of heat flow, that is meter square. The rate of heat flow transfer by conduction is in watts. Thermal conductivity of the body is expressed in this. Area is in this. So, dt by dx is a temperature gradient, which is K by m. So, the heat flux is defined as the rate of heat flow per unit area is the heat flux. What is heat flux? The heat which is applied over a unit area. The heat flux, if it is high, then what will happen? Heat will be applied here. For example, let us apply joules per, we will take it centimeter square, right, centimeter square, joules per maybe millimeter square, same joules. The area is reduced. So, now what do you say? The flux is increased. So, the heat flux is defined as the rate of heat flow per unit area. This is the unit area, or the amount of heat transfer per unit area per unit time is given in watt meter square. So, heat flux is nothing but Q. Small q is defined as Q by A. Q is nothing but the rate of heat flow, by A is the area. So, you can see this is the area. So, the heat is flowing from T1 to T2. Right. So, the equation heat flux can be expressed as minus K into the gradient. So, the Fourier law is very important. So, please keep that in mind. There can be some questions in the Fourier's law of conduction. So, there are only two formulas, Qs equal to minus K A into dx by dt, this is a gradient, Q is equal to minus K conductivity into delta T. Thermal conductivity is a measure. So, conduction, whatever happens is the rule law we are saying. But now, when you are trying to go to a market and buy a material, you are supposed to specify it in terms of some value. For example, give me a piece of give me a pen of 20 centimeter diameter or 20 centimeter length. Give me a ice cube of 1 meter cross 1 meter cross 1 meter, right. So, the dimensions are there. So, when we say 1 meter, 1 meter, 1 meter, so it is size, so it is in meters. Same way, the temperature also has to be measured and it has to be constant for a given material at a given temperature. So, the parameter for measuring the thermal response of a given material is conductivity. Why is it important? Conductivity can expand the material. Your MCBs, whatever work in your home, works on the concept of thermal conductivity, or the wire which is used as a fuse wire which is used also works on thermal conductivity. When there is more current drawn, there is heat generated. Moment there is heat generated, it thins or it softens and then it yields. And by doing so, it brings a disconnect between the live wires. So, and the second thing is thermal conductivity is very important because what is the length of the stirrer I use in the kitchen? Right. So, that also plays an important role, because if the heat gets conducted very fast, very slow, if it is very fast, I should keep a longer handle. So, that also depends on thermal conductivity. So, thermal conductivity is one of the properties with which you can evaluate a material for heat related applications. Thermal conductivity is a measure of the ability of a substance to conduct heat. It is the quantity of heat passes through a quantity of material of unit thickness with unit heat flow in unit time. So, this is very important, heat passing through a quantity of material of unit thickness with unit heat flow area in unit time, when the unit temperature difference is maintained across the opposite faces of the material. This is very, very important. Friends, keep every point is important. Heat passing through a quantity of material, a given area, right, quantity of material of unit thickness, right. So, we are talking about area is only xy plane. Now, they talk about also thickness. So, now they are talking about volume, quantity of material of unit thickness with unit heat flow rate in unit time. So, you are trying to measure within 1 minute what is the, so unit time with unit thickness with unit heat flow, right. When the unit temperature differs in maintained across the opposite faces of a material. So, this is one phase, this is the other phase, this is what there is in top phase, bottom phase, right. Thermal conductivity depends on the nature of material and its temperature. Larger the value of K, thermal conductivity, higher will be the amount of heat conducted by the substance. So, that is why if you see in many of the spoons, you will have a steel and then you will have a non-conducting material. This will be non-conducting, this will be conducting. So, we are least bothered. So, we always touch the non-conducting part. It is the characteristics or a transport property of a material through which the heat is flowing and varies with temperature. The thermal conductivity of a solid are higher than the thermal conductivity of the liquid, and liquid are having higher thermal conductivity as against the gas. Why? Because the atoms are not compacted. So, if the atoms are not compacted, the heat cannot travel very fast. So, the conductivity of a solid is always higher than liquid and gas. So, that is why we say metals are good conductors of heat. So, here also you can see aluminum conducts faster. stainless steel slightly slower, right. So, each material has its own thermal conducting property. So, now conduction through a plain wall or a slab. So, this is the hot phase, this is the cold phase, right. There is a wall in between. The wall has a thickness of dx. So, here the length is 0, here the length is L. So, the distance width of the wall is L, right. This is a hot phase and this is a cold phase. So, now you would like to know, when I apply a temperature T1 on the hot phase, what will be the temperature in T2 and how much time will it take. So, that is what we can try to find out by the conduction plain wall slab. Consider a wall is made of a material of thermal conductivity K is, and the uniform thickness X is the uniform thickness, and a constant area. So, this is a wall. So, the wall has an area. So, this is area, length into breadth. Right. So, it has a uniform thickness x, right. It has a uniform thickness x and it has a cross section area A. Assume that K is independent of temperature, conductivity is independent of temperature, and the wall area is very large in comparison with the thickness. So, we are trying to take a large area board, the thickness is low. Assume that you have a paper, right, large area and the thickness is very low, right. So, that is what we say. The area of the wall is very large in comparison with the thickness, so that heat loss from the edges are negligible. So, the hot phase is T1 and the cold phase is T2, and both are isothermal surfaces at all points of which the temperature is the same. So, here also throughout the temperature will be T1, here also throughout it will be T2. The direction of the heat flow is perpendicular, the heat flow is perpendicular to the area, to the wall, and the T varies in the direction along the x direction. So, x is equal to 0 to x is equal to L. So, as it is a steady state, Q is constant along the path of heat flow. What is Q? Q is the rate of heat flow. So, as in the steady state, Q is constant along the path of heat flow. The Fourier's law equation can be integrated over the entire path from 0 to L. So, Q conducting of a wall is nothing but minus K times A into dx by dt, where this is done by Fourier's law of conduction. Now, it varies, the variable is in one are from x or x and t are variable. So, from x equal to 0 to x equal to L, Q dot conduction wall dx is equal to T1 minus T2. So, here you have minus term K times A delta T. So, the conduction of this plain wall is expressed by this form K times A T1 minus T2 by L. So, by rearranging the equation, by rearranging this equation, so KAL can be replaced by L by Ka, right. So, this also can be replaced, Ka can be brought down and other things. So, you can do, and then what happens, you get this equation. So, it is nothing but thermal resistance of the wall is, the thermal resistance of the wall is L by Ka. So, it is T1 minus T2 by R wall. The reciprocal of the resistance is called as conductance. So, this is resistance conductance, which for heat conduction is referred as 1 by R, which is Ka by L. Both the resistance and the conductance depends on the dimensions of the solid as well as on the thermal conductivity, a property of a material called delta. So, what did we try to find out? We used Fourier's law, which we studied. We were trying to take a wall, wall or a slab. We were trying to measure a temperature T1, T2 and the wall thickness. So, now what we will do is, we have found out what is the conductance which is happening, and then 1 by R is the resistance. So, conductance is nothing but 1 by resistance, that is what we are writing it here. So, and then R is nothing but L by Ka. So, now if you want to do, conductance will be Ka by L, that is it. So, that is what we have written it here, right. So, it is nothing big. both the resistance and the conductance depends upon the dimensions of a solid as well as the wall on the thermal conductivity. Now, this is a single homogeneous material. This example was a single homogeneous material. Now, what I want is, I would like to have multiple materials. For example, like a sandwich, you have a bread on top, you have something in between, then a bread on the bottom, right. So, assuming that there is a sandwich, each of this material has its own property. So, that is what is composite slab. Consider a flat wall constructed of a series of layers of 3 different materials K1, K2 and K3, A, B and C. K1, K2, K3 are the thermal conductivity properties of the material of which layers are made. Then the thickness are delta 1, delta 2 and delta 3 respectively. So, let delta T1 be the temperature drop across the first layer and delta T2 be the temperature drop at the second layer and delta T3 be the temperature drop at the third layer. So, let delta T be the temperature drop across the entire wall. So, what we are trying to say is, we are trying to say this is T1 drop, T2 drop, T3 drop. It can be uniform, it need not be uniform. So, the overall temperature drop will be delta T. So, T1, T2, T3, T4 be the temperature at the faces of the wall. T1 is the temperature of the hot face. T1 is the temperature of the hot face. T4 is the temperature on the opposite side of the hot face, that is a cold face. Assuming that the layers are in excellent thermal contact. So, between these two there can be air as a contact, between these two there can be welding, right. So, it is nothing like perfect. So, but here we assume that is perfect contact, are in excellent thermal contact. Let the area of the composite be A. So, the overall temperature drop is delta T is delta T1, delta T2 plus delta T3. In the steady state condition, the heat flow is Q in the area for all the layers and it is constant. The equation of heat transfer through these layer is given by Q is equal to K1 times A T1 minus T2 into delta 1 for first layer, second layer, third layer. Now, the temperature difference across these layers from the above equation can be represented as T1 minus T2 equal to, I am rearranging this equation, Q times delta 1 by A1. So, just to rearrange. So, here it becomes okay. So, what we are trying to do is T1 minus T2 by delta 1 into K1 times A is equal to Q. So, now T1 minus T2 is going to be, so we are going to take this delta to the top. So, it is going to be Q, I am known quantity. So, I am going to take delta 1 by K1 times A. So, T1 minus T2, T1 minus T2 is going to be Q times this, and then T2 minus T3, the next one, T2 minus T3 is going to be this. I am rearranging the equation, T3 by T4 is this. So, by adding all this equation, T1 to T4, adding all the equations. So, then what happens? I try to take the Q which is out, I take it out, then I try to plot for individual layer thickness divided by the thermal conductivity, the area is constant. Now, what do? I try to keep Q and then I try to take this at the bottom. So, where R1, R2, R3 be the thermal resistance offered by 1, 2 and 3. I am converting into the resistance. If you go back and see, here also what did I do? I converted into resistance. So, here also what I will do is I will convert into resistance. Q1 is equal to T1 by T4, that is what is the temperature drop. So, that one divided by delta 1 K1A. So, what is K1A? K1, so we know that 1 by R is equal to Ka by L. How did we get this? We got this from here. 1 by R is Ka by L. So, we just represent it. So, that is nothing but delta by Ka. So, now all of these are changed into resistance. So, Q is the heat which flows and then you get the temperature difference by this formula. Moving on to conduction through a plain cylinder. Examples, you can think of a pipe wherein which you have a inner wall and outer wall thickness. The difference between a cylinder and a pipe is, the thickness of the sheet whichever is there, the thickness of this material will be thin in a pipe. So, they will have an outer diameter, inner diameter. The difference between the outer diameter and inner diameter, the values will be small, and if it is longer, it is a pipe. If it is shorter and thicker, then it is called as a cylinder. So, it has lot of applications. Boilers, it has they take it as a cylinder, right? Thick cylinder, thin cylinder, they take all those things. So, now we will try to see how can we extrapolate what we saw for a flat surface, for a composite surface, how can you take it for a cylinder. So, consider a thick walled hollow cylinder with an inner radius R1 and an outer radius R2. The length of the cylinder is L. Let the temperature inside and outside the surface be T1 and T2. T1 is at the innermost and T2 is at the outermost. So, naturally T1 is higher than T2. The heat flows from the inside of a cylinder to outside. According to Fourier's law, which we saw, we have minus Ka dt by dr, where T is the temperature, R is the radius. So, dt by dr is the thermal gradient, which has a unit of K by m. So, the QR, whatever we are doing, is the heat flux. So, QR or Q. Q is the heat flux in the radial direction, which is watts per meter square. Then the conductivity is watt per meter Kelvin. Then a cross section area will be meter square, and dt by dr is K by m. Separating the above equation, what did we do is we just moved dt out and dr here. So, we brought it as Q by 2K pi L. Where did this 2K come? Because it is a cylinder, right. Integrating T equal to T1 and R equal to R1 to T equal to T2 and R equal to R2, then we try to get T2 by T1 is equal to minus Q times 2 pi KL, natural logarithm of R2 minus natural logarithm of R1. Now, I take the natural logarithm out. So, it becomes R2 by R1. So, T2 minus T1 is equal to minus Q 2 pi KL natural logarithm of R2 by R1. Now, when we try to swap over, so T1 minus T2 is equal to this minus sign goes away, natural logarithm of R2 by R1. So, finally, this is represented by this way. So, 2 pi k goes here into T1 minus T2 equal to Q times ln R2 by R1. Therefore, the final equation can be written as this: 2 pi k L T2 minus T1 divided by natural logarithm of R2 by R1, where this entire thing, natural logarithm of R2 by R1 divided by 2 pi k L, becomes the resistance. Resistance is 1 by conductance. So, resistance. So, the same thing what we did for composites and for plain wall, we are now using the same concept and trying to do for plain cylinder. So, we can also try to extrapolate for a composite cylinder. Composite cylinder will be R, you will have inner radius R, and then inner radius plus their thickness, whatever we have is Ri plus 1. Then we can try to go to R2, then it is R2 plus, this is R2, this is R2 plus 1. So, here the total resistance will be R1, R2, which goes on up to Rn, and Rn can be expressed in this form. Rest all is the same what we see in the plain cylinder. So, the overall heat transfer for a composite cylinder will be T inner minus T outer divided by the total resistance. This derivation and form of Fourier's law for composite cylinder is widely used for calculating heat loss in a pipe with multiple insulation layers and other layered surfaces. For example, you can think of having a water tank in the top of your house, and here you get a connection made through a pipe to your house. So, now in a cold winter day in North India, the temperature goes somewhere between 10 degrees Celsius to 15 degrees Celsius in the night, and in summers it goes somewhere between 42 degrees Celsius to 48 degrees Celsius. Now, what is the way about? You try to take a pipe and then you try to put a insulation on the pipe. you try to put an insulation on the pipe. So now what happens is it is nothing but a composite cylinder. So the Fourier's law of composite cylinder are widely used for calculating heat losses in pipes. Heat loss means when you are trying to push in water, heat loss. The other way around is because it is exposed to the atmosphere, tank is exposed to the atmosphere, so the temperature is very low. So now what we do is we try to increase the temperature here and send it through it. So calculating heat loss in pipes with multiple insulation. So if you see here, you can have one more round of insulation, and then you can try to find out what is the conduction which happens through the layered surface. Now let us move to the next topic of convection. Convection is a combined heat transfer mechanism in which the thermal energy is conveyed through both molecular conduction within a fluid and macroscopic motion of the fluid as the flow past a solid boundary. Whenever a temperature difference exists between a surface and an adjacent liquid, for example, the liquid can be air or gas, as a thermal boundary layer developed, the fluid motion carries enthalpy away or towards the surface, thereby redistributing the energy throughout the bulk. This process underpins the phenomena ranging from the gentle circulation of air in a sunlit room to a high-speed cooling of a turbine blade in a jet engine. So, this convection phenomena happens from a gentle circulation of air in a sunlit room. So, that means to say you have a glass panel, you are sitting inside the room, to a high-speed cooling of a turbine blade in a jet engine, making convection center to discipline as diverse as meteorology, oceanography, chemical processing and electronic thermal management is very important for convection. So, convection, you can see there is a convection phenomena happening, right. The hot water goes up, the cold water comes down, there is a vortex which is getting created. So, I will go back. Whenever a temperature difference exists between a surface, you take a surface and this is a surface and the adjacent liquid, you are immersing it in water or you are keeping it in air. Adjacent liquid, a thermal boundary develops. So, between this and the next there is a physical boundary. So, in the same way there is a thermal boundary which gets established. A fluid motion carries away the enthalpy, heat carries away the enthalpy or brings in the enthalpy towards the surface. Therefore, the redistribution of energy takes place throughout the bulk. At the heart of convective transport is the simultaneous presence of two intertwined mechanisms. One is conduction, in which energy diffuses through random molecular collision, and advection, in which the fluid parcels physically carries internal energy as they migrate. So, at the heart of convective transport is the simultaneous presence of two intertwined mechanism, conduction and convection. So, it is conduction will happen moving, advection in which the fluid parcels, physically carry internal energy as they migrate. Inside the boundary layers adjacent to a heated or a cold wall, inside the boundary layer adjacent to the heat. So, assume that this is the boundary layer. Inside the boundary layer adjacent to the heated or a cold wall, conduction dominates because velocity approaches zero at a non-slip surface. Further away, advection prevails as faster moving fluid streams entrain and mix parcels of different temperature. So, this is what it is, parcels of mixed temperature, advection. So, that is what this is called as conduction, advection, it has become convection. The composition between these effects determine the local temperature gradient, the thickness of the boundary layer and ultimately the overall rate of heat removed or supplied. Determines the local temperature gradient, the thickness of boundary layer. Suppose if the thickness is very large, then there is going to be a different phenomena. When the thickness is very small, there is going to be a different phenomena. It depends upon the local temperature gradient and the thickness of the boundary layer. So, as we were talking about, we were always saying that it is very much used in meteorology, oceanography. So, here we will see the free convection. So, free convection is natural convection is also known as free convection. It is the process by which the fluid motion and heat transfer occurs naturally. I boil a egg, he keep it at the free atmosphere. So, without free atmosphere, without any help, there is a transfer of heat. Without the help of any mechanical device, fan or pump, the heat gets transferred. The cold air comes. So, this is a hot egg. The cold air comes, hits the hot surface, and it tries to become lighter and it moves further away. Cold air are heavy, so it comes and hits the egg. So, egg tries to increase the temperature, then this cold air becomes warm. Warm air are lighter, so it goes in the top. So, here is a heat transfer happening. So, natural convection is also known as free convection, is a process by which the fluid motion and the heat transfer occurs naturally. There we do not apply any energy. The movement is driven by the difference in the fluid density caused by temperature. Cold is down, hot is top. And then when the cold moves up, the hot, if you put it inside a confined body, this hot goes up. Then when the hot goes up, the cold tries to fill in the hot. So, then hot is filled everywhere. Now, it tries to circulate. When the fluid is heated, such as air near the hot surface or water near the heat source, it becomes less dense and then rises. The cooler dense fluid then sinks to take its place, creating continuous circulation pattern. This natural flow helps transport heat from the warmer region to a colder region. Free convection, for example, a room with a space heater. The air closest to the heater warms up, becomes lighter and rises to the ceiling. The cold air from the above moves down to replace it and establish a loop of warm and cold air. Convection happens. So, although the process is slow and less efficient than forced convection, it is important in many everyday situations where quiet passive heat transfer is very much needed. Because if you forcibly apply an energy there, then the same heat transfer is going to happen for which you have added work to it, such as in residential heating, solar collector and natural ventilation systems. We design it like that. Engineers must consider room layouts, surface orientation, temperature difference when designing the system that rely on natural convection, as these factors significantly affects its performance. So, what is the mechanism of free convection? In natural convection, the fluid motion occurs by natural means such as buoyancy. Buoyancy force are developed due to the density variation in the fluid, hot cold variation in the fluid caused by the temperature difference between the fluid and the adjacent surface. Since the fluid velocity associated with natural convection is relatively low, the heat transfer coefficient encountered in natural convection is also low. So, heat transfer coefficient, transfer of heat is also low. So, now let us move to forced convection. So, hot body, cold air, warm air. Now, this is happening naturally. Now, I force air. Forced convection is a mode of heat transfer in which the fluid motion is induced by an external source such as a fan, pump or a blower. Unlike natural convection, where fluid flow is driven solely by temperature difference, forced convection uses mechanical device to move the fluid, allow it to have a much faster and more controlled way of heat transfer. Right? This method is especially used in applications. That is why if you see, there are fans in your laptop. There is a fan which forces air onto the processor and the heat is extracted. So, there is a fan. The same way you have a fan in the compressor. You have a split AC, you will have a blowing station inside your house and the compressor outside your house. The compressor will have a big fan. This big fan will try to force air and hit it on the compressor such that the heat whatever generates because of compressing, which we saw in the jet engine cycle and all, compression. So, there will be a lot of heat because pressure and temperature increases when you try to. So, that heat has to be extracted. So, that is where we use fans, right. For example, in car radiator, cooling fluid is actively pumped through a narrow tube absorbing heat from the engine and transferring it to the surrounding as a fan forced air over the radiator fins. So, in order to extract heat, that is why in radiator you will always, or in AC unit you see lot of fins will be there. These fins are used for doing a larger surface heat transfer. Similarly, in laptops and desktop computers, small fans pull cold air across the hot components like CPU and GPU, preventing overheating. So, that is why in initial days they used to say keep your desktop computer in an air conditioned unit. Even today, if you have a very big server, in order to maintain the server's temperature to 18 degrees and 12 degrees, 14 degrees, we always have it inside an air conditioned room of a controlled atmosphere. Because the fluid is pushed with a greater velocity over the heated surface, the rate of heat transfer increases, making forced convection highly effective. The heat transfer coefficient in forced is much higher than the natural convection, which means engineer can design compact and high performance thermal systems using the forced convection. So, if you see there, when you try to heat, the high dense molecules, they come down, the low dense molecules go up. So, there is a transfer. Forced convection allows for better control over flow rate, direction and temperature gradient, making it ideal for small scale and large scale industrial processing. So, we burn, there is water which gets heated and it circulates, and then after a period of time it tries to maintain uniform temperature. It is used in jet engines, refrigeration systems, nuclear reactors and even food processing equipments where precision temperatures are to be maintained. We use the forced convection. The efficiency of a forced convection depends on the factors like fluid velocity, surface area, fluid property and the turbulence of the flow. So, these are all important properties which dictate the forced convection. Fluid velocity with which it is flowing, surface area large, this is why we have AC's fins, that is their radiator fins, then fluid property, so hot to cold, and the turbulence of the flow. So, how if it is lamellar flow, it is just flowing on top. If it is a lamellar flow, it will be a smooth flow. When it is when there is disturbance, it is a turbulent flow. This turbulent flow can extract more heat. So, the convection, the rate of heat transfer in convection is described by Newton's law of cooling, where Q is equal to H A Ts minus T infinity, where Q is the amount of heat transfer per second, where H is the heat transfer coefficient, A is the total area, S is the surface temperature, T infinity is the fluid temperature. So, by using this you can try. See, we saw Fourier's law of conduction, we saw convection is Newton's law of cooling in convection. The heat transfer coefficient H is much higher for forced convection as compared to that of a natural convection. Engineers use this formula to design the system and make energy efficient systems. The last one is going to be radiation. The radiation refers to the transport of energy through space by electromagnetic waves only. The first two, conduction through atoms. Next is it can be through atoms or it can be through a advection, right. So, it is very important, you should know this one. At the heart of conduction transport is the simultaneous presence of two intertwined mechanisms. One is conduction, you know conduction, hot rod, conduction, molecule wise motion, random motion, vibration, collusion, conduction. And then you have the other one is advection, in which fluid parcels physically carry internal energy as they migrate. So, here in radiation, it passes through space by electromagnetic waves. You can have a vacuum or you can have a space also, depending upon the electromagnetic waves as a means of transfer of energy from a source to a receiver. The mechanism of heat transfer is photon emission, and the mode and the energy transfer does not require any medium. It can be through vacuum, it need not be in vacuum, right. So, it does not need a medium. The significance of this is that the radiation will be only mechanism for heat transfer whenever a vacuum is present. This is the only way, right. So, examples of heat transfer by radiation: transfer of heat from sun to earth, the use of energy from sun in solar heating, the heating of a cooling room by radiation electric heaters. So, when we talk about radiation, there are properties like absorptivity, reflectivity and emissivity. So, for example, if you have a clean polished surface, when the heat is hit on it, it reflects, right. Any substance receives and emit energy in the form of electromagnetic waves. When the energy emitted by a heated body falls on a second body, it will partially absorb and partially reflect back and partially transmit back. So, what we are trying to say is, when there is heat hitting, one way is it travels, that is partially transmitted. So, this is transmitted. Then the other way is it is getting absorbed. The third one is it is getting reflected. So, this is an electromagnetic wave. So, you can have transmitted, you can have reflected, and then the next one is absorption by the medium itself. It is only the absorption energy that appears as a heat in the body. So, whenever sun rays falls on a human, you try to absorb heat. You put a glass mirror, it tries to reflect. It absorbs heat, it can absorb and transmit. For example, microwave allows through a glass bowl, it transmits microwave. It allows the microwave to pass through where you kept the food and water, right. One is it transmits, it absorbs. Transmit is it enters and it exits also. There are ceramic material where it is transparent. It is the only absorption energy that appears as a heat in the body. The incident radiation is equal to absorption, then it is transfer outside and then heat reflected. This proportion of the incident energy that are absorption, reflection and transmitted depends on the characteristics of a receiver. So, radiation, fraction of the incident radiation on the body that is absorbed is absorbivity. So, which gets absorbed is absorbivity A or alpha. Then which gets reflected, which is called as rho. Which gets transmitted, it is called as tau. So, the energy balance about a receiver on which the total incident energy falls is unity. So, what they are trying to say is, when the radiation falls, so radiation is equal to rho plus alpha plus t, tau, whatever it is, which is unity. So, for an opaque material, A plus R equal to 1, tau equal to 0. What is opaque? Which does not allow anything to transmit. So, for a perfectly transparent material, so tau equal to 1, AR equal to 0. Reflection will not be there, absorption will not be there. For a non-reflecting surface means, suppose if the surface is rough or if there is an oil film on top of it. So, then what happens? The reflection is 0 and R is equal to 1. Perfectly reflector A is equal to 1, perfectly absorption, so that is a black body can be there. So, black body will be A equal to 1, R equal to tau equal to 0. It neither reflects nor transmits, but absorbs all the radiation incident on it. So, it is treated as an ideal radiation receiver. The black body radiates maximum amount of energy at a given temperature. Lamp black is the nearest to a black body which absorbs 96% of the visible light. Both absorptivity and emissivity of perfectly black body are unity. So, in the radiation, you also have monochromatic emissivity and monochromatic emissive power. It is a radiation. Monochromatic means single wavelength. Monochromatic emissive power. It is the radiation energy emitted by a body per unit area, per unit time, per unit wavelength. It is denoted as E lambda, which is given by a formula watts per meter square into micrometer. So, this is micrometer, single wavelength radiation. What comes through a heated body, it need not be a single radiation, single monochromatic radiation. But here we are trying to talk about a phenomena called as monochromatic emissive power. Monochromatic emissivity is the ratio of monochromatic emissive power of a body to that of a black body at the same wavelength and at the same temperature is emissivity. So, when we try to look at the physical property, we try to talk about specific heat or the heat conduction and also emissivity. Reflectivity also we talk. There are bodies which are called as gray bodies. We know black, the other one is gray. A gray body is defined as a body whose absorptivity of the surface does not vary with variation in temperature and the wavelength of the incident light. A gray body is defined as a body whose absorptivity of a surface does not vary. The absorption, whatever happens on the surface, does not vary with variation in temperature 20 to 30, 40, 50 and wavelength of incident radiation. So, here we were talking about monochromatic single wave. So, here immaterial of the variation in temperature and immaterial of the incident ray. So, we have a gray body, that is a body having the same value of monochromatic emissivity at all wavelengths is called as the gray body, and the emissivity is independent of wavelength, which is very important. See, when you try to incandescent bulb, electricity is passed, the coil is heated, it radiates light, right. So, that need not be in single chrome, it can be in any wavelength. So, friends, I am sure this lecture would have been a great learning with lot of practical examples I gave. So, to recap what we saw in this lecture, what do you understand by heat transfer in thermodynamics? Name and explain the modes of heat transfer. We studied the phenomena of conduction, then Fourier's law, different types of conduction. Then we saw how does the conduction happen on a plane wall, composite wall, in a cylinder. What do you understand by convection? Convection has conduction plus advection. So, it is conduction here. Then there are two types of conduction, forced and free. Then finally, we saw radiation. Friends, this lecture has lot of examples and you can also see various examples. I would like to give you a small exercise. Please try to look at this one and this topic and try to give 10 examples of each of them which you do not know, but you are knowing it for the first time. 10 different examples for each of these phenomena, right, and wherein which you try to understand new concepts through it. These are the reference materials which we have used for making this slide. Thank you very much.